speed control method. I told you that it is very simple. That is the advantage of stator voltage control method. And the disadvantages are starting torque decreases when you decrease the voltage, and it will not give wide speed control range. So that is the advantages and disadvantages in stator voltage control method. Next we will see rotor resistance speed control method. Next we will see the frequency control method. First we will complete the stator side speed control method, then we will come to the rotor side. Okay, that is better. Now we have varied only the magnitude of the input voltage, and we understood how the speed is varied. Now next, if we vary the frequency of the stator voltage, speed can be varied or speed can be controlled. So what is the governing equation? Rotor speed is equal to 1 minus S into 1 F by P. So F is the stator frequency, P is the number of stator poles. So if you vary the stator frequency, if you increase the frequency, rotor speed can be increased. If you decrease the stator frequency, rotor speed can be decreased. Right? So this is the stator frequency control method. So conventionally, how to vary the frequency of the stator? To vary the frequency of the stator, conventional method is not very easy. There is no conventional method to vary the stator frequency. Only we have to go with power electronics control method. Right? So that you will be studying in third year. Just you know that to vary the stator frequency, power electronics converter only can be used. The name of the power electronics converter is cycloconverter. So using the cycloconverter is one of the power electronics converters that is used to vary the stator frequency. That is used to vary the stator frequency. Conventionally, it is not feasible to vary the frequency. Conventional mechanical based system, it is very highly difficult. So one go with power electronics converter. The name of the power electronics converter is cycloconverter. Now, by keeping the magnitude of the voltage constant, if you vary the frequency, how that will reflect in the torque slip characteristic. So that we have to see now. So if you see the torque slip characteristic for varying frequency, see, actually, you can derive the torque equation in terms of stator frequency, but derivation is not very important. But some inference directly we will take from the derivation. So when you derive torque equation in terms of frequency, the maximum torque you will get proportional to V by Fd whole square. You will get like this. And your starting torque also, it is proportional to maximum torque. This relationship we can derive, but derivation is not much important for you. Only we will take inference from the derivation, and we will understand how the torque slip graph will vary when you vary the frequency. Now you are keeping this V constant. In frequency control, you are keeping the V constant. Only you are changing the frequency. Here, you assume some base frequency. The base frequency is nothing but that is the rated frequency. For example, this is 50 Hz. Now, you can draw the torque slip characteristic for base frequency or for rated frequency 50 Hz. So, normal torque slip characteristic, you will get it. Slip is equal to 1. The torque slip characteristic, sometimes it is called as torque speed characteristic. Anyway, you can call the graph. And this is the hypothetical boundary line. Here slip is equal to 0. Here NR is equal to S. Okay. So you will get the graph like this. So this is for the base frequency. Draw a view. This is for the base frequency. So I will get the graph like this. Then you draw one more torque speed characteristic for the frequency F1 that is lesser than your rated frequency. For example, let me take this is 25 Hz. If you draw the graph by keeping the frequency 25 Hz, you will get the graph like this. Here you are reducing the frequency, you are keeping V constant, the maximum torque will increase because frequency it is in the denominator, the maximum torque will increase, so you will get the maximum torque point here. This is for the frequency F2. The different color. Mass is equal to E by F T square. In starting torque is proportional to T. So, excuse me for the diagram. This is the torque. So, if you draw, okay. So the frequency is decreased, maximum torque will increase. The starting torque is proportional to maximum torque directly. So starting torque will be increased, maximum torque also will increase. This is for the frequency F2. Okay. And here the important point what we have to note down is that the synchronous speed corresponding to this frequency F2 also will change because you are changing the frequency. Synchronous speed is 120 F by P. So for the base frequency, synchronous speed will be NS1. For the base frequency, it is NS1. When the frequency is reduced to 25 Hz, for that you will have synchronous speed that is NS2. The hypothetical point that will vary. Right? This is drawn for the frequency F2. Now you draw the torque slip characteristic for another frequency. This is greater than F rated. Here frequency can be more or less when compared to the rated frequency, nothing will happen to the machine. But the voltage alone, you cannot have more than the rated one. That will create insulation problem, right? So only variation in voltage below the rated voltage or till the rated voltage only is possible. But that is not the case in frequency. Either you can go above or you can come below. So this is F2 is greater than F rated. Let me take 75. Now you are increasing the frequency, so the maximum torque, no, it will decrease. Starting torque also will decrease. So you will get the graph like this. So this is NR is equal to, sorry, this is NS, this is NS1, this is NS1, this is NS2. So NS2, that is the synchronous speed, corresponds to 75 Hz, and NS1, that is the synchronous speed, corresponds to 25 Hz, and NS, that is the synchronous speed, corresponds to 50 Hz. So here, this is for frequency F2, this is 75 Hz. This is for frequency F1, that is 25 Hz. Okay. So this is the torque state characteristic we will get when you vary the frequency by keeping the voltage constant. Right? So here, what you can observe is that the maximum torque is keep on changing. That is the first observation. So what is the inference? Maximum torque is keep on changing. Starting torque is keep on changing. The slide is saving. And the synchronous speed corresponding to various frequencies, no, that is also changing. That is the inference. So what is the inference? Maximum torque changes. Starting torque also changes, and synchronous speed also changes. These are all the inferences for Stator frequency control. But what about the speed control range? If you look at the speed control range, to understand that, you have to draw the load torque speed curve. For example, if you assume this is my load torque, you assume the load torque is constant like this. This is my torque speed characteristics of load. So this is the torque speed characteristics of the load. This is the load torque. Load torque I am assuming constant for understanding purpose. So where are the operating points now? I told you that operating points are the intersection of machine torque and the load torque. So this is one operating point. This is another operating point. This is another operating point. So this is for 75 Hz and this is for 50 Hz rated and this is for 25 Hz. So if you look at the speed control range, it has increased. which is widened. So this is your speed control range. This is your speed control range. So if you look at the speed control range, it is increased. So here speed control range is increased, and it is widened. So these are all the inferences we can from the frequency control method. Another inference is that one more inference also is there. This is 3, this is 4. Fifth inference is that if you want to get the speed control below the rated speed control, if you want to have below the rated speed control below the rated speed, below the rated speed means that is corresponding to 50 Hz. Okay, speed control below the rated speed means it is corresponding to 50 Hz frequency, right? And speed control above the rated speed, above the rated speed, that is more than 50 Hz, are possible in frequency control. Are possible in frequency control. You see here? So this is below the speed control. This is above the speed control. Both are possible here. So below the speed control, you can very well correlate with armature control method in DC motor. It is very much similar. Above the speed control also it is possible. That is very much analogous to field control in DC motor. So below the rated speed, above the rated speed, both are possible in frequency control method. That is not possible in voltage control method. Only below the rated speed it is possible. Above the rated not possible because you cannot increase the voltage more than the rated one. That creates insulation problem. So these are all the inferences from voltage control and frequency control. Till now, any doubt? If you have any doubt, you can ask me. Any doubt? Now, we will proceed further. When you vary the voltage magnitude alone by keeping the frequency constant, or when you vary the frequency alone by keeping the voltage magnitude constant, there is one common problem in electrical machines. There is one common problem that will occur in electrical machines, right? What is that problem? What is that problem? You take the EMF or voltage equation in induction motor. EMF or the voltage equation in induction motor is very much similar to transformer EMF sorry, transformer EMF or voltage equation, because induction motor, no, it is called as rotating transformer. So the EMF equation or the voltage equation, whatever we have derived in transformer, it is applicable for induction motor also. So what is the EMF equation? EMF equation is 4.44 frequency, flux and the number of turns. Okay, frequency and number of turns. So with respect to primary, with respect to stator side, you can write E1 is equal to 4.44 F5N1. And E1 is approximately equal to V1. So V1 is replaced with E1, V1 is replaced with E1, or E1 is replaced by V1. So V1 becomes 4.44 F5N1. Okay, V1 is equal to 4.44 F5N1. You bring the frequency to the left hand side. So V1 by F is equal to 4.44 pi N1. So here 4.44 is constant. N1 is the number of turns in the stator. So that is also constant. So I can write V1 by F is proportional to pi. Or simply I can write V by F, the ratio of voltage with respect to the frequency is proportional to the flux in the machine. Now, in the stator voltage control method, if you decrease V, that is what I have written here. If you decrease V, this line, if you decrease V, flux will reduce because V is directly proportional to the flux. Right? If you increase V, this is not possible at all. So no need to worry about increasing V. So I think we can take off this. This is not possible. Okay. So if you decrease V, flux is decreasing. Increasing V, it is not practically affordable. So don't worry about increasing V, the flux will increase. That is not taken care. Now, in frequency control, if you keep voltage constant, if you vary the frequency, for example, you are decreasing the frequency, flux will increase. Okay. So here, decreasing the frequency, flux will increase. When you increase the frequency, flux will decrease. Okay. So what we can understand from this, either when you vary the voltage magnitude or when you vary the frequency, the flux is changing. Right? The flux is changing with respect to change in the voltage and frequency. In any electrical machine, always it is desirable to maintain the flux constant at its rated value, because when you operate the machine below the rated flux, the efficiency of the machine will reduce because you are not completely exploiting the potential of the machine, or the torque production that is proportional to the flux only. If you operate the machine below the rated flux, so definitely the net output from the machine will decrease. That leads to decrease in the efficiency. When you operate the machine more than the rated flux, right, unnecessarily we have flux more than the requirement. It produces heating effect in the ferromagnetic core. That will increase the core loss. Again, that will reduce the efficiency of the machine. So always it is desirable to maintain the flux at its rated value, and it should be maintained constant. Right? It should be maintained constant. Right? That is what here I have written. Flux has to be maintained constant. You can see here the flux has to be maintained constant. This is what the requirement in induction motor. How to do this? You vary V and F proportionately. When you increase V, that is not possible. When you decrease V, decrease frequency. Right? Proportionately you vary both the parameters. When you increase the frequency, right, V should be increased, but V cannot be increased. So in that case alone, we will have this flux variation problem that we'll understand while we are studying the torque slip characteristics. Ultimately, our desired requirement is flux has to be maintained constant. So you vary V and F proportionately with respect to each other. If you decrease frequency, you decrease V also in proportion with F, right? So that the flux can be maintained constant. Right? When it is not possible, when you increase the frequency, you cannot increase the voltage. In that case, maintaining the flux is not possible. Even though that is our desired requirement, it is not possible. Right? So these are all the disadvantages or common disadvantages for both voltage control and frequency control. Right? For both voltage control and frequency control. So in order to overcome this problem, people have come up with another speed control method that is called D by F control method. So when you vary V, F also is varied. That is called D by F speed control method. So how to vary V and F proportionately with respect to each other? Only by using the power electronics converter it is possible. The name of the power electronics converter is inverter. Okay? Right? So inverter is used to vary the voltage and frequency proportionately with respect to each other. Right? So not much discussion about inverter is required at this level. Only you note down the name. Inverter, that is the power electronics converter, is used to vary the voltage magnitude and frequency of the stator supply. Okay? So that is your V by F control method. Now if we vary V and F proportionately with respect to each other, how we will get the torque slip characteristic? So if you draw it, you will get the torque slip characteristics like this. So the one I have indicated in red color, the one graph I have indicated in red color with a thick red color. So this graph, okay, that is the graph drawn for rated V and F. That is for rated. Now you are decreasing the frequency. When you decrease the frequency, voltage also is decreased in proportion to the frequency. So when you do that, V by F ratio, no, it will be maintaining constant. It will be maintaining constant because your T max is proportional to V by FD whole square. So when you decrease the frequency along with decrease in the voltage in proportion with respect to each other, suppose you are decreasing F by K times, you can decrease the V by K times. So K get cancelled with respect to each other. So the maximum torque remains the same. I think the relationship I have written here, no, I think that is not holding good. Maybe this, please excuse me for this. Don't take this relationship. Okay? Don't take this relationship. T max will be proportional to P max will be proportional to P by F the whole square. T starting torque will vary. That alone I can say here. Will vary when you vary the frequency. When you decrease the frequency, T starting, maybe I can write say like this. TST, maybe it is proportional to what I can say. Maybe it is the relationship I don't have for that. So only I can write like this, because the derivation, the relationship is very complex. So qualitatively we can write like this. Starting torque will vary with respect to frequency. You note down like this. With respect to frequency. Okay. And here, when frequency decreases, TST increases. Maybe here it is inversely proportional. When F increases, TST decreases. I can write like this. Your starting torque, maybe it is inversely proportional to F. Okay. Starting torque, maybe it is inversely proportional to F. We'll see whether that is coming through here also. Yes. So the next graph, you decrease the frequency and you decrease the voltage also in proportion with respect to each other. This is the graph you will get. Graph 2. Okay. So the starting torque increases. So it means that your starting torque, I can write it is proportional to 1 by S. Okay. Maximum torque is proportional to V by F to the whole square. Starting torque is proportional to 1 by F. So you will get the graph like this. Till you decrease the frequency. So you will get the family of graph like this. So this is graph 3, graph 4, graph 5. You will get the graph like this. Okay. So rated V by V and F and decrease V and F. Further, again you decrease V and F further. Again you decrease V and F further. So the constant K gets cancelled with respect to each other. So you will get the families of graph like this. Right? This is for below the rated voltage and frequency. Now, I am increasing the frequency now. When you increase the frequency, voltage cannot be increased more than the rated one. So, at this case, it is highly impossible to maintain the maximum torque constant and also to maintain the flux constant. So, definitely no, the maximum torque will decrease. This is the maximum torque will decrease for increase in frequency, and voltage cannot be increased because of insulation problem. So, in region D, flux is decreasing because you cannot maintain the flux constant, because V by F only, no, you are increasing the frequency. So the phi is proportional to V by F. When you increase the frequency, you are keeping this is constant. When you increase the frequency, flux will decrease and maximum torque also will decrease, right? Maximum torque also will decrease, and you will get the graph like this. You will get the graph like this. Right? You will get the graph like this. So this will be like this, and this will be like this, and this will be like this. If you want, you can extend. Okay, I will extend and then show. Because starting torque is inversely proportional to frequency. So when you increase the frequency, starting torque will decrease. So you will get like this, you will get. Okay. So in region A, flux is constant, right? And the speed control is below the rated speed. In region B, flux is decreasing, the speed control is above the rated speed. So region A, that is very much similar to armature control of DC motor. Region B, that is also very much similar to field control of DC motor. So this is the torque field curve for various V by S values. So that is what here I have written. Region A, when V and F decreases, speed decreases, maximum torque remains constant, starting torque increases. So this is for below the rated speed control. Below the rated speed control. Okay. And region A, V by S constant flux, same, we are continuing in region A only. And this is very much similar to armature control. At present, don't take this word, do not understand this. So simply you can take in region A, V by F is constant flux operation, maximum torque constant, and this is very much analogous to armature control in DC motor. In region B, V by F is not constant, it is not possible. So here flux is not constant. Okay, is not constant, and this region, sometimes it is called as field weakening region or flux weakening region. This is very much similar to field control method in DC motor. So here speed control is above the rated speed. Above the rated speed. Okay. So that is what here I have written. Okay. And what about the speed control range here? So for that you have to draw the load torque graph. So this is my load torque graph. So you see here, this is my operating point, this is my operating point, this. So speed control range in V by F control also it is more. The speed control range in V by F control also it is more. Right? So this is your V by F control. Now if you compare all the three, just we compare all the three control methods with the significant point. Okay. This is voltage control, this is frequency control, this is V by F control. Here, speed control range is narrower. We are comparing all the three control methods using the significant point. Speed control range is narrow. Speed control range is wider. Here also speed control range is wider. Why it is narrow? Because the synchronous speed, NS, is same for all the voltages. Is same. So the graph if you draw, all these points will come and accumulate at one point only. That is why your speed control is very narrow. Because synchronous speed is same for all the different voltages. So every end of the graph will come and converge at one point. So your region is very narrow. But when you vary the frequency, synchronous speed will change. Okay? And you will get the graph like this. So since the synchronous speed is changing, the speed control is wider. Here also it is applicable as same with respect to frequency control. That is why your region is narrow in voltage control method and it is wider in frequency control and V by F control method. Okay. And second case, speed control below the rated speed is possible. Here both are possible, below and above. Here also same thing, it is applicable. And third one, flux is not constant. Similarly, flux is not constant. Here, at least flux is constant in the below the rated speed region. At least flux is constant. At least flux is constant in below the rated speed region. Below the at least below the rated speed you can maintain the flux constant. Above the rated speed you need, then it is not possible to maintain the flux constant. But at least below the rated speed, at least you can get that advantage. Right? So these are all the comparison between all the three controls. Significantly, we have compared all the three control methods. So with this, I stop the today's class. If you have any doubts, you can ask me. Till now, any doubts anybody is having? Okay, you can ask me. V control, V by F control, F control. Any doubts? You cannot increase the voltage more than the rated one because that will create insulation problem. Understood? See, we need to have constant flux, but it is not possible in above the rated speed region. It is not possible. Right? Because when you increase the frequency, you cannot increase the voltage. That will create insulation problem. So that you cannot avoid that.